Let us start with the next lecture, that is a rate based on rate constant and rate law. Now, if you consider a reaction like this, if you consider the reaction, a general reaction, where the coefficients are given in small a and small b, and capital A and B are the reactants, to give C and D as a product. So here you can see this is an irreversible reaction. When I write this forward arrow, it means it is a irreversible reaction. Now where this A, B, C and D, this A, small a, B, C, D are the stoichiometric coefficient. These are the stoichiometric coefficients. These are stoichiometric coefficients for the reaction of reactants and products. Of reactants and products. I'll write in short R and P. R means reactant and P means product. Now reactions can be elementary. There are two types of reactions. So reactions can be, one is it can be elementary. Elementary reactions are those which occurs in single step. So elementary reactions are those which occurs in single step. Elementary means single step reaction, remember. Okay. And the other type, that is a complex reaction. So complex reactions are those which occurs in number of steps. Most of the organic reaction, not all, most of them, most of organic reactions are complex reaction, means they occur in stepwise. Elementary reactions are the single step reaction, and complex reactions are occur with the number of steps. Okay. Now elementary reaction, I can give a very simple example. That is the titration we used to perform in the laboratory. NaCl plus H2O. It is very simple reaction. So nothing more can be expected from this reaction. If the product is fixed and water molecule, NaCl and H2O, and it occurs immediately or in a single step. Whereas most of the organic reaction where we need to use some catalyst, intermediate products are there, and then you will be getting the final product. Number of organic reactions examples can be given, but I'll restrict myself. I'll not discuss more about this. Only just you understand, complex reaction are those which occurs in number of steps. Now, in such cases, the rate of this reaction, it is proportional to concentration of A. Rate will be also proportional to concentration of B. These are the reactants, isn't it? So rate is proportional to concentration of A and concentration of B. Means in short, you can write rate is proportional to concentration of product of concentration of A and B. This is very simple. Now here it is, rate is dependent on the concentration of A and concentration of B at that moment. At that moment. So this is important here, at that moment, and not on the initial amount of the reactant. So the rate is dependent on the concentration of the reactant A and B at that moment, and not on the initial amount. Okay. So this is what we call as the instantaneous rate of reaction, not on the initial amount of reactant. Now, this is what we call as the instantaneous rate of reaction. Now, what does it mean actually? It can be explained by giving a very simple example like this. Now, let us discuss this in very simple way. Now, if I have got 10 rupees with me, and I am giving you, out of this 10 rupees, I am giving you 10% of this. So 10% of this means I'll give you 1 rupees, isn't it? Now, I am now left with, after giving you 1 rupees, I left with now 9 rupees, isn't it? Okay. Now, out of this 9 rupees, if I again give you 10% of this 9 rupees, it means that I'll be giving you 0.9 rupees, 10% of 9. Okay. Now I left with now 9 minus 0.9. So it is found to be equals to 8.1. Now I have got this 8.1 rupees, and if I give you out of this 8.1 rupees 10% of this, so that will be 0.81 rupees and so on, isn't it? Means here what am I doing? I am giving you each time 10% of the amount that I have at that moment. Initially, I started with 10 rupees. Then I left with 9 rupees. Then now I left with 8.1 rupees. If I minus this 8.1 minus 0.81, so whatever is that, from that I can give you 10% and so on. So this continues. So the rate, it is dependent on the amount which is left with me at that moment, and that is what we call as the instantaneous rate of the reaction. So I tried to explain it with a simple example. This is the meaning of this sentence. Is the rate of this reaction, it is dependent on the concentration of A and P at that moment and not on the initial amount. So this I tried to explain with the simple example. Is the rate will be dependent on the amount which I have at that moment and not with the initial amount. This is my initial amount, or this might be the initial concentration of the reactant. But as we proceed further, it goes on decreasing, isn't it? So the rate of the reaction for instantaneous rate, it will be dependent on these amounts and not on the initial amount, which I have left after consuming some of the reactant. So it means that way. Now, so I can conclude from this that the rate of the reaction, it depends on the amount of the reactant at that moment and getting converted into product in 1 second. So nine time limit should be there. So whatever is the amount you have at that moment, which is getting converted into product, which is getting converted into product in how much time? In 1 second. This is called as the rate of the reaction, isn't it? Means the rate of the reaction, I can write the rate of chemical reaction, rate of chemical reaction at given temperature. No doubt temperature and concentration are the governing factor for the rate of the reaction. At given temperature, it may depend on concentration of one or more reactants and products. Okay, so this is what I try to explain by taking this simple example. Now, how do we represent the rate of the reaction in terms of the concentration? So what is this rate law actually? Up till now, we discuss about the rate of the reaction. Now we come to the, I just revise the things just to approach for the rate law. Before that, I just explain in short about the rate of the reaction. Now, what is this rate law? This rate law, it is nothing but the representation of, it is the representation of rate of reaction. Now, I hope you understood what is rate of reaction. We have been discussing this since the last 2-3 lectures. Rate of reaction in terms of concentration of reactants. Remember, so the concentration of reactants is very important when you represent the rate law in terms of concentration of reactants. So these underlined words are important. Representation in terms of the concentration of the reaction. What? That is the rate of the reaction. This is called as the rate law. Now, the rate law expression for the reaction can be written in this way. Now, if you have this reaction in front of you, this is the general way I'll be writing. If you have this reaction in front of you, how will you write the rate law for this? No doubt this is to be considered as an elementary reaction or the single step reaction. Okay, so this is only applicable to the elementary reaction. When it is a complex reaction, you need to think in different way. We'll discuss this later on. So if this is an elementary reaction, how will you write the rate for this? So rate, it is proportional to concentration of A raised to A and concentration of B raised to small b. So what are these A and B? These are nothing but the stoichiometric coefficient, isn't it? So these are the stoichiometric coefficient for this. Now these A and B, small a and B, are also called as order of the reaction. Remember. So this order of the reaction concept, no doubt we'll be discussing later on, but just initially when you come across this A and B, this is nothing but the order of the reaction. So I'll explain this order of the reaction in detail in due course of time. We'll just focus our discussion up to the rate law at this moment. Now for the complex reaction, as I told, this is the rate law. This is rate law for the elementary reaction. So for the complex reaction, rate for the same, if you consider the same reaction as a complex one, means if the same reaction is going to happen in number of steps, how will you write the rate law for this? So you can write that as concentration of A raised to X and concentration of B raised to Y. Now again, this X and Y, these are the order of the reaction. So this is the order of the reaction with respect to A. This is the order of the reaction with respect to A, and this is the order of the reaction with respect to B. I wrote in short with respect to. Okay. So X and Y is nothing but the order of the reaction in terms of or with respect to A and B. Now, as I told, in complex reaction, this is for the complex reaction. In case of complex reaction, now, before coming to this complex reaction, let us again go back to this elementary reaction. Now, in elementary reaction, stoichiometric coefficient, what are these? These are the A and B. So, stoichiometric coefficient A and B will be its order of the reaction. So, whatever is the value for the A and B, that will be the order of the reaction for elementary reaction. Or in case of the complex reaction, the addition of these two, X plus Y, that will be the order of the reaction. Now, you might not understand how does it X plus Y to be written. So let us now not discuss about this order of the reaction. We'll discuss this later on. Just you remember that is X and Y may or may not be, this X and Y may or may not be equal to stoichiometric coefficients A and B. Remember, that is why it is written instead of A and B, it is written here X and Y. Just to indicate that X and Y may or may not be equal to stoichiometric coefficient A and B. Means X and Y may or may not be equal to X and Y. It means that. Now, why this is may or may not be equal to A and B? For elementary reaction, it is same, but for complex reaction, it may be or may not be equal to X and Y. As I told earlier also, in complex reaction, it proceeds in number of steps. Now, out of this number of steps, one of the step may be a slowest one. Okay, so that slow steps, if it is occurring in 2 or 3 steps, out of these 3 steps, suppose the slow step is there, means first step is a fast one, second is a slower one, and third is again a faster one. Now this slow step, which I told that is the second step, suppose now this slow step will decide the rate of the reaction, what we call as the RDS, that is rate determining step. You have came across this word rate determining step in halogen derivatives, where you study SN1 and SN2 mechanism. So whenever we study the mechanism, this RDS, that is rate determining step, is always there. That is the slowest one which determines the rate of the reaction. Now, if you look at this reaction like this, just by looking at this reaction, it is not possible to determine the order of the reaction. Just by looking at them, you cannot predict the order of the reaction. You will have to determine the order of the reaction experimentally. It means that, what does it mean? It means that X and Y, what is this X and Y? This is the X and Y. These X and Y are the experimentally determined quantities. X and Y should be determined experimentally. So these are the experimentally determined quantities. We'll have to perform some experiment and then only we'll be knowing the values for this X and Y. Okay, so these are the experimentally determined quantities. Now, in short, R will be equal to, if you remove this proportionality sign, you can write K into concentration of A raised to X into concentration of B raised to Y, whereas this K equals to rate constant. Okay, so this is nothing but the rate constant. Now, rate constant, it is defined as the rate of the reaction. So rate constant, it is nothing but the rate of the reaction. What is this rate constant? This is the rate of reaction which would have if all the concentrations or all the concentration were set to or set equal to unity. So what does it mean actually? What is the meaning of this sentence? Were set to unity. Now we have come across this concept of rate constant. No doubt K is equal to rate constant, but what does it actually means? This is the rate of the reaction which would have, whatever is the rate of the reaction, which would have if all the concentration. Now I told that the rate of the reaction, it is dependent on the concentration of the reactants. Okay, so of course all the concentration means concentration of the reactant when it was set to unity, means unity means 1. Okay, now I'll explain this with the again very simple example. Now again I'll take the same example. Now if I have 1 rupees, okay, and if I give out of this 1 rupees, I want to give you 10%. So it will be how much amount I'll give you 0.1 rupees. Okay, now out instead of 1 rupees, now if I have 10 rupees, and if I want to give you again the 10% of this, so how much I'll give? 1 rupees. Okay. So what I'm doing here? I'm keeping this 10% constant. Okay. So this 10% which is remaining constant. So from 1 rupees, I am giving you 0.1%. From 10 rupees, I am giving you 1%. Now if I have 7 rupees, so from this 7 rupees, if I want to give you 10%, so it will be 0.1 into 7, isn't it? 0.1 into 7, so it comes out to be 0.7 rupees. Okay. Now now I have 8 rupees. Now 0.1 into 8, so now I'll give you 0.8 rupees. So what does it mean? It means actually I'm giving you the 10%. I wrote in some different way only. So what I am doing, I'm just keeping this 10% quantity constant. Here also 10%, here also 10%, here 10%, here 10%. Now, if I have instead of this 9.2 rupees. So from this, if I want to give you 10%, so what will be its quantity? That is 0.92%, 0.92 rupees, sorry. Okay. So here again same thing I am doing, that is I am keeping this 10% constant. Now similarly, I'll go to the next slide. Similarly, if in the reaction, I'll apply this concept to the reaction now. A is getting converted into product. Only one reactant is there and getting converted into product. Now, if I say this A, which is a reactant here, so this reactant is unity. means 1. So how much from this unity, how much from reactant, from that reactant is consumed, from that reactant is consumed for what? For getting converted into product. Consume, it is called as the rate constant. I hope you understood. This is the rate constant. With this constant quantity which I am giving you each time, that is a 10% here. Every time I am keeping this constant, this is called as the rate constant. When the condition is that if the reactant is unity means 1, how much from that 1 or unit concentration the reactant is consumed, this is called as the rate constant. Okay, now proceeding further, we need to calculate the units for this rate constant. Okay, now again I'll write the reaction, same one. If I have this reaction, elementary reaction like this, so rate can be written for this as K into, I hope you understood what is now K into concentration of A raised to X into concentration of B raised to Y. Now we'll be discussing order of the reaction later on. X plus Y, this is nothing but N. This is the order of the reaction. I'll tell you afterwards. I'll discuss in detail about this order of the reaction. Now, just try to write this equation in terms of K. K will be equal to rate divided by concentration of A raised to X and concentration of B raised to Y, where we know that rate of the reaction is nothing but the concentration divided by time, change in the concentration. Okay, so change in the concentration with time, that is nothing but the rate. We know this too. Now substitute the value for rate in this equation. So for this same equation can be written as K will be equal to, instead of rate, I'll write here concentration per time. Okay, into 1 divided by concentration raised to N. Okay, means instead of this A raised to X, A raised to X and B raised to Y, I wrote here concentration raised to N. N means what? N is nothing but X plus Y. Now, where this concentration, I'll write here, where this concentration raised to N is nothing but the concentration of A raised to X into concentration of B raised to Y. Now, for what we are doing this, we need to find the units for this rate constant. Now we have these equations in front of you. Now let us proceed further for the calculation of this. Now here, wait a minute, I'll add one slide here. So when you, okay, now taking the SI units for this, taking SI unit of concentration. What is it? That is equal to moles per liter. All of you know this. And for time, it is second, which is denoted by S, small s. Now, if the reaction is, I'll try to write in a tabular form so that you will understand more clearly. Now, units of rate constant. Units of rate constant. Okay. Now, if your reaction is zero order, as I told, we'll discuss this order of the reaction in detail further. Just you assume that if the reaction is zero order, means order is 0. So what will be the rate of the reaction here? That will be equal to mole per liter divided by second into 1 upon moles, mole per liter raised to 0. 0 means this is the order of the reaction. Okay. So this whole quantity will be equal to 0. This will become equal to 0. So what will the unit for this? It will be mole per liter per second. If the order of the reaction is 0, this is the unit for rate constant. You will need this information when you perform the calculation part. Okay. Now, if it is a first order reaction, okay, if the reaction is first order, I'm just putting these values in this equation, which I wrote in the earlier slide. This concentration upon time into 1 upon concentration raised to n. Okay, so I'm using this equation to calculate these units. Concentration here, it is moles per liter. Time, it is taken in second, into 1 upon concentration raised to n. N means the order of the reaction. I hope you understood this. Okay. Now, if it is a first order reaction, so you can write here 1. Now, again use this same equation, K equals to. Now, for this you can write here moles per liter. Wait a minute. If you can write for this mole per liter divided by second into 1 divided by mole per liter raised to 1. What is this 1? This is the order of the reaction. I am substituted the value of n here. This n equals to 1. So this will get cancelled out. So now you are left with second inverse. So this is the unit for the first order reaction. Now if the reaction is a second order, if it is a second order reaction, so it will be 2, and again substitute here moles per liter, that is the concentration, divided by time. Time we are taken in second, into 1 divided by mole per liter. Now here value of n is 2, so I can write here 2. Okay, so you will get here mole inverse liter and second inverse. Okay, so I'll just explain how does it come on the next slide. Wait a minute. I'll add one slide. You will be more clear with this. Now for the second order, this is the thing initially, that is concentration per time into 1 divided by concentration raised to n. So moles per liter raised to 2, because n equals to 2. Now you can simplify this as moles per liter divided by second into 1 divided by square of this. So you can write this 2 times into moles per liter. Okay, so this will be again equal to 1. So this will get cancelled out. This and this thing will get cancelled out. So you are left with 1 by S into, so this will go up liter S into mole. So you can write the same thing as mole inverse liter and second inverse. So this is the unit when the reaction is second order. Okay, so you need to remember these units. You should understand how do you calculate the rate of units for the rate constant. Okay, now this is the way you go for the calculation of the rate constant. Now here